Hi everyone! Today I wanted to talk about a really cool device in electrical engineering called the transistor. So the transistor basically revolutionized the field of electrical engineering in the 50s and basically allows us to have all of the technology that we're used to today. So phones, computers, basically any kind of computing is made possible by the invention of that transistor. So let's get right into how that works. First, I wanted to give a little bit of background on electricity itself. And I'm sure you've heard this before, all of matter is made up of tiny particles called atoms. And those atoms consist of smaller positive and negative charges. So the positive charges are called protons, and but what we really care about is the electrons, which are the negatively charged particles of the atoms. And that's because electrons are more prone to move than protons, and movement of electrons is what causes electricity. That really is the definition of electricity. So an electron will move, one, if it's free to do so, we'll talk about that in a second, and two, if there is a positive charge that it is attracted to somewhere else in a system. Negative charges are attracted to positive charges and are repelled by other negative charges. So that's sort of the basis of what causes electrons to move in the first place. So if we look at a way that this is commonly represented, which is an electric field, we can see that our electric field is basically the movement that a positive charge would go through in a system. So we can see here that positive charges are attracted to the negative charge and are repelled by the positive charge. So another way that we can think about this is that there is a potential of an electron to move in the system. So there is something called a potential difference between the positive and the negative charge. And this is also called a voltage. So as I mentioned previously, even if there is a potential difference in the system, in order for there to be electricity, we have to have mobile electrons. So there have to be electrons that are free to move. And this comes from different bonding configurations that atoms can be in. So atoms can either have metallic or non-metallic bonding structures. So in non-metallic bonding structures, atoms can either give up an electron to another atom, or they can share electrons. So those electrons are kind of locked in place by the protons of those atoms. However, in metallic bonding structures, there's sort of these proton cores, and surrounding that is this sort of sea of free electrons. So that sea of electrons is mobile. So if a potential difference is applied, say a positive charge down here, then those electrons would tend to move towards that positive charge, and that causes electricity. So that is why metallic structures are conductive, while these non-metallic structures are called insulators, so they do not conduct electricity. So there is a third class of material called semiconductors. So as the name would imply, these sort of have conditional conductance. So they are neither metallic nor non-metallic in that they are strictly insulators or conductors. So let's take a look at how that works. Let's take a look at this silicon lattice here, where each of these proton cores is able to sort of share these 8 electrons with the surrounding atoms. So how this works is each sort of proton core locks the surrounding 8 electrons into place, and it really can't handle more than 8 electrons, and that's a chemistry problem. But imagine if we replace one of these silicon atoms with a phosphorus atom. So phosphorus has 1 more electron than silicon does. So even though this proton core has 1 more positive charge as well, it adds an electron to the system that the phosphorus atom is not able to lock down. So this becomes a mobile electron because all of these atoms are currently locking the maximum number of electrons into place that they can. So this type is called a semiconductor, and it's called a N-type semiconductor because electrons, which are negatively charged, are able to move. So this is called N-type. So if we have semiconductors which are N-type or have negative charge carriers, you can imagine that we would have the opposite, or positive charge carriers, or P-type. And what that means is if we again take a look at our silicon lattice, and we instead replace one of the silicon atoms with an atom that has one less electron than silicon, say boron, then instead of having an extra electron to sort of add to the system, it's missing one of these electrons. And so that causes a what's called a hole, which an electron can move to fill. So that electron from the silicon atom might move into that hole there, which might cause that electron to move there, which might cause that electron to move there. And since we do have movement of electrons, that's conductance. So we have a partial conductance caused by this addition of a different type of atom into a lattice. So these additions of either usually phosphorus or boron or something that has either one extra electron compared to silicon or one less is called doping. So doping causes semiconductance. Okay, so what would happen if we put an N-type semiconductor right next to a P-type semiconductor? So I have this drawn here, and you can see that the P-type has those holes floating around, while the N-type has those floating electrons that are sort of free to move in the system. However, what if we were to apply a potential difference like this? So specifically a potential difference in the form of this battery, which has a positive terminal here and a negative terminal here. So if we attach the negative terminal to the P-type material and the positive terminal to the N-type material, then as you can imagine, these electrons will be attracted to this positive charge, while these positive holes would be attracted to this negative charge. However, since the positive positive charge is attracted to this negative charge as well, we sort of reach an equilibrium where these electrons might shift a little bit this way and these holes might shift a little bit this way, but there won't be any more movement of charge through this system. So an application of a potential difference in this way actually causes a blockage of electrons from moving. However, if we were to apply a different potential difference, so basically if we actually reversed the orientation of that battery, so that the positive charge was connected to the P-type and the negative terminal was connected to the N-type, these electrons would actually be repelled by this negative charge and would jump into this P-type material and recombine with some of these holes. Similarly, these holes would be repelled by the positive terminal and would be sort of sent across this way. So we would get a flow of electrons which would jump to the P-type and be attracted to this positive terminal, which would cause a flow of electrons through the system in this sort of loop as long as the battery continues to have charge. So the use of P-type and N-type semiconductors to do this is known as a P-N junction, which is also known as a diode. So these are just characterized by what we just talked about, which is the movement of electrons in one direction. So this can only conduct current if it is in this configuration, and if we were to turn that diode around, then no current would flow. So there would be no flow of electricity in this loop. So what would happen if we put a P-type semiconductor between two N-type semiconductors? So let's take a look at that. So again, what would happen if we applied a couple potential differences or voltages like this? So here we have two batteries, or two potential differences added to our system here, where the lowest voltage would be here and the highest voltage would be here. Because the potential differences are battery stacked this way, so there would be some midpoint voltage in between these two batteries. So let's take a look at how these charges would move. Let's do this by first ignoring sort of this half of the system. So let's ignore this N-type material in this battery at first. So if we take a look, we have a P-type material connected to the positive end of this battery and an N-type material connected to the negative end of the battery. So this looks like a diode, which we just discussed. So basically, we'll have electrons that flow across this P-type and into this positive end of the battery. However, I did draw this the p-type material as sort of a thinner layer than the other two on purpose, and that's because as these electrons move, they will cross over the p-type material sort of on their way to act as a diode, and be attracted to this positive end of the terminal here, which is pulling electrons from the system. As we sort of discussed previously, when we have a positive end of a battery connected to the n-type material, it'll pull those electrons, and then since we're having electrons provided by this battery, we're able to get current flowing through. So even though we do get some current which flows through this material like a diode, actually the bulk of the electrons will cross the p-type material into the n-type material. So by applying a mid voltage to this p-type material, we're actually able, so sort of if we are able to draw electrons, a small amount of electrons from this p-type material, we get a lot of electrons moving across this transistor. And yes, this is a transistor. So this is known as a NPN transistor. So you can see it drawn a little bit differently here. And this is called an NPN transistor because it is that N-type, P-type, N-type junction gig. So basically, if we take a look at our other drawing again, so now I've labeled sort of like this pink as electron flow. So you can see that a little bit of electron flow here, but the bulk of the electron flow is between these two, this region of the semiconductor. So in this way, this transistor can act as an amplifier. So basically, by applying a voltage here and getting sort of a little bit of current sort of inserted into this transistor, we're able to get a massive current flowing through this transistor. Or I guess current flows the opposite way of electrons, by the way. So electrons would be flowing this way, but that means that the current value would be this way. So again, amplifier. A little bit of current in this way causes a much larger current through this loop here. And so that's one way that a transistor can be used as an amplifier. Another way we can think about this is sort of to go back to the diode analogy. If we were to apply a sort of different series of potential differences to our NPN transistor, we wouldn't get any current flow through the system because one of the PN junctions would be off. So that diode would be sort of reversed and wouldn't let any current through. So if we think about sort of using voltages, we can use our voltages to amplify current, as we've seen here, but also use it to block it. So in this configuration of voltage, you can see that we have current flowing through the system here. However, if we were to apply a different sort of voltage configuration, then we would get zero current flowing through here. So in this way, we can also use voltages not only to amplify our currents, but also to act as sort of a switch, so to turn off current between here and here. So just to sort of label these transistor parts, this here is known as the transistor base. This is the emitter of the transistor, and this is known as the collector of the transistor. Now that I've talked a lot about how these transistors work, both as an amplifier and a switch, we can go observe these behaviors in the laboratory. Alright, welcome to the lab. So here I have an NPN transistor that I've stapled to this piece of paper. So you can see that it has those three terminals, the middle of which is the base, and one is the collector and one is the emitter. I've actually built an amplifier circuit here. So if you recall, our NPN transistor, we have the base, the collector, and the emitter. And in order to get amplification, we need to apply, so instead of using a battery, I'll be using a power supply and applying these voltages directly. So this I applied as 0 volts, applied 2.5 volts to the base, and applied 5 volts to the collector. So let's take a look. Alright, so here is the circuit. If we take a closer look, we can see that I've set up the transistor and the applied voltages as well as LEDs. So what those will do is the more current coming through, the brighter they will light up. I've also included some resistors, and that's so that we can dissipate that current going through, because if we don't do that, we'll be at risk for causing an electrical fire. So we want to avoid that. So I'm going to turn off the light so that we can see that diode on the base is actually lit. So there is a small amount of current going through, but remember that it's being amplified by quite a bit. So we can see how bright that LED is between the collector and emitter just by looking at it. Here is the circuit functioning in the dark. And you can see that LED on the base is barely lit, while the LED on the collector is quite bright. So we are able to see that amplification just by applying a mid-range voltage at the base. We're able to see that massive current amplification between the collector and the emitter. I've turned the lights back on, and now that we've seen the transistor act as an amplifier, recall that it can also act as a switch. So by controlling the voltage at the base, we not only can cause a current gain between the collector and the emitter, but we can also use the voltage at the base to switch on and off that connection. So if I were to drop the base voltage to 0, you'd see that LED turn right off. So I can turn the LED on and off just like a switch. Well, that's all I have to say about transistors for now. These are fascinating electrical devices that make possible a lot of different technologies that we take for granted today. Specifically, its application as a switch has made computing the field that it is today. So I hope you learned something from this video, and thank you for watching.